If you look on the back of a frozen food packet, you'll find a small but very easy to read chart featuring some star-like symbols and some durations. This is designed to tell you how long you can store food for in a way that doesn't require you to know too much technical detail about your freezer's temperature. If your freezer is a one-star freezer, usually a small ice compartment more than a proper freezer, you can keep it for a few days. If you have one with 4 shiny stars on it, you can keep it for 3 to 4 months or even longer. In practice though, we usually just bung stuff in the freezer and forget about it. This practice probably makes intuitive sense to us. After all, it's frozen, as in frozen in time. So surely those Findus crispy pancakes from 1998 must still be fine, right? Well, like all chemistry, it's a little more complicated than that. Food is not a chemically pure substance. Fats and alcohols have very low melting points, so we can still have liquids sloshing around even in a freezer. Even where the concentration of those isn't high enough to properly suppress the melting point enough to remain liquid, we can still have a reactive chemical mess inside food. And despite what you may have thought back in school, chemical reactions can definitely happen in the solid state. They're usually slow, yes, or require high temperatures, but being frozen solid isn't actually a barrier to chemistry happening. What's happening in a freezer is simply that we're lowering the temperature to slow down chemical reactions, not completely stop them. We're removing much of the thermal energy required to chemically react. Even in a freezer, even frozen solid, the food will chemically react and degrade, just very, very slowly. Hence the wide range of times on the back of a packet, ranging from a few days to many months. Let's look at those times in some detail for a minute. At the highest freezer temperature, only a few degrees below zero, use it within 3 days. Then a week, then a month, and then 3 or 4 months. We can even add in 24 hours if it's in the fridge. This is a huge range of time, spanning nearly 2 orders of magnitude. If we plot the same data against a rough estimate of the temperature involved, it looks like a very steep but regular curve. So the question is, why? Why that curve, and can we simplify it a little? This curve is explained by the Arrhenius equation. This is really old, late 19th century chemistry. It's an exponential function which relates the temperature and the activation energy of a reaction to its rate constant. This is basically a measure of how intrinsically fast a reaction is. There's a short derivation that proves that we can use a reaction time instead of this constant. This is good for us because we have a set of reaction times and temperatures on the back of a food packet. First, a very brief aside into one of the things we see a lot in physical chemistry, the straight line graph. We're interested in straight lines connecting two variables as that means something constant and consistent is happening. And the gradient of that line, or how much it goes up for a given amount that it goes across, will be a meaningful and useful value. We can achieve the same results by fitting nonlinear equations like the Arrhenius equation to raw data, but if we expect the graph to be straight, the trend is a little easier to check. We make the Arrhenius equation linear by applying the natural logarithm to both sides of the equation. The result doesn't look quite like a straight line yet, because now we need to know what to plot to make it a straight line. And by looking at the equation, we can see that the y must be a natural log of the rate constant or reaction time, and the x must be the inverse of temperature. So we can go ahead and do that. We can make sure the reaction times are in a consistent unit. In this case, we'll pick days, find the natural log of that, and we'll also find the inverse of temperature as well, adding 273 degrees to each because it needs to be on the absolute temperature scale. Do 1 divided by all of that. And then we plot the numbers and straight line. Give or take a bit of experimental error and some fudging around. And if we look at the gradient, we'll find that this must have an activation energy of about 97 kilojoules. About right for a very average chemical reaction. So how literally can we take that result? Unfortunately, not too much. That it forms a straight line is good, and that the gradient is in the range that we expect is very good, but remember, this isn't rigorous data. These are not times that have been set based on well-quantified reaction extents. They're rounded off for ease of use, and they're set in a way that prioritizes food safety, so they're cautious estimates. So the data is not perfect, there's going to be a lot of error here, but nevertheless, this small chart comes entirely from chemical reaction kinetics.